Hello everyone. The last lesson on the topic glass. So let's consider Pyrex glass or Jena glass. Raw materials: silica, small amount of alumina, some oxides. Here you can see a composition of raw material and properties. Substitution of alkali and basic alkali earth oxides, of the soda glasses by boron and aluminium oxides results in a low thermal coefficient, high softening point and excellent resistivity, shock proof. Of course, high chemical resistance, and uses in industrial pipeline for corrosive liquids, judge glasses, superior laboratory apparatus, etc. Aluminosilicate glass. Raw materials: 5% more of alumina. Addition of alumina makes glass heat resistant. Composition of aluminosilicate glass you can see here. Properties: exceptionally high softening temperature, chemically durable, resistance to hydrolysis, offered by moisture due to high surface area. Uses: high pressure mercury discharge tubes, chemical combustion tubes, specific domestic equipments, and fiber glass. Optical quartz and opal glass. Optical glass. Raw material: phosphorus and lead silicate. Properties: low melting point, soft, chemical resistance, durability lesser than ordinary glasses. Uses: optical lenses. Quartz glass. Raw material: crystalline silica fused at 1900 degrees Celsius. Properties: outstanding resistance to thermal shock and chemicals. Uses: special lab ware, crucibles, reaction tubes. Opal glass. Raw material you can see here, and properties: translucent white or milky glasses, transparent when in liquid, solid when cooled. And now topic glazing. What is the glazing? Glazing, which derives from the Middle English for glass, is a part of a wall or window made of glass. Glazing is when you paint a thin layer of minerals and glass onto a fired or unfired ceramic piece. The act of installing glass in windows, doors, or fixed openings, in practically it would be the actual installation of a piece of glass within a frame. History. Glasses have been discovered to have been used in the decoration of ceramics. As far back as the early Egyptian period, powdered glass was originally used as the base of historic glasses. Minerals and water-soluble salts were added which altered the color and texture of the final product. Glass is an essential material in buildings due to its combination of transparency and durability. Most buildings are designed and constructed with windows, and besides admitting daylight, they can enhance the appearance of the building from both inside and out. Glass has been increasingly popular with architects, and it has been used extensively in many urban buildings, including some very tall structures. Many modern and striking buildings now incorporate large areas of fenestration, while offering many attractive and beneficial aesthetic and technical advantages. The use of glass does bring certain problems in its wake. Traditional single-glazed windows can be regarded as areas of weakness in many respects. We have looked at the physical properties of glass earlier, and from this we can see that while glass is not a good conductor of heat, at least compared with metals, it doesn't have a modest value of thermal conductivity. Therefore, heat losses through a large area of single glazing will be unacceptably large, as we now live in an energy conscious world. Another thermal problem is that of solar gain, or the greenhouse effect. Incoming sunlight is short-wave radiation, and heat radiated back to the windows from warm objects inside the building will be longer-wave radiation. Ordinary glass is transparent to incoming sunlight, but relatively opaque to the heat energy trying to exit the building interior. If we have large areas of windows, when solar gain can make the building interior uncomfortable for the occupants, energy-consuming air conditioning is not the desired solution. Glass has a low value of fracture toughness, which makes it susceptible to impact by flying objects and to the blast waves generated by nearby explosion should one occur. Therefore, the principal problem with glass windows come under the following headings: thermal problems, sound or acoustic problems, and fire and impact problem. Thermal problem. Single glazing has a very high U value at around 5 watt by square meter C, and therefore a large amount of heat can be lost through single glazed windows. However, new buildings are required to be fitted with double glazing, and this reduces the heat losses by around 50%. The current need for energy conservation means that even a value of 2.5 watt by square meter degrees are too high to achieve the very low glazing or value required by the Code for Sustainable Homes. We must have recourse to triple glazing with krypton gas, infill and low emissivity glass. By this means, we can reduce the U values to 1.2 watt by square meters degrees, or perhaps a little lower. Visible light is only a proportion of the total energy received from the sun. Part of the insulation is heat energy. Low emissivity glass ensures that more of the thermal component is kept out. The diagrams illustrate this. In plots light transmission percentage against total radiation transmission percentage, the performance envelopes for body tinted glass, reflective glass, and low emissivity glass are shown here. The next problem, sound and acoustic problems. In urban areas, traffic noise can be very intrusive through single glazed windows, particularly if the window frame is ill-fitting. Sound insulation can be markedly improved by double glazing. Strictly, the spacing of two panes of glass for sound insulation is wider than that required for thermal insulation. But, nevertheless, double glazing for the purposes of thermal insulation will deliver an impressive improvement in sound insulation too. And fire and impact problems. Windows are vulnerable in fire situation because of thermal shock, which causes cracking and shattering of the glass. If a window is lost, this will enable two things to happen. Flames can escape from the room or enclosure and thus spread the fire. Air can enter the room or enclosure and thereby ventilate the fire. That is, allow oxygen to reach and therefore sustain the fire. If the pane of glass doesn't shatter, heating by the fire may cause the glass to thermally soften. And the pane of glass can sag out of the frame with similar effects to those mentioned above. that is ventilation and escape of the fire. To prevent a cracked glass from falling out of a window pane, wired glass is commonly used. This ensures that a cracked window pane remains in place, preventing both escape and ventilation of the fire. To prevent softening glass from falling out of the window frame, strips of intumescent material can be located along the edge and of the glass inside the window frame rebate. As the fire hits the intumescent strips, they will swell and therefore exert a positive grip of the edge of the pane, thus preventing it from failing. Windows are particularly vulnerable in the event of the explosion. Explosions produce blast waves which move outward from the center of the explosion at the speed of sound. The shock front of a blast wave is a very thin zone of raised pressure, twice atmospheric or more, followed by the rarefaction wave, which is a region of low pressure, below atmospheric. When a blast wave strikes a window, it may crack the glass and in a few cases blow the broken glass into the building. In many cases, however, the pane absorbs the pressure and bulges inwards like a tennis racket. Thank you very much. And now repeat a new word. Pot furnace, tank furnace, annealing, shaping, melting, amorphous, silicate, silicon, sodium, potassium, calcium, lead, zinc, lime, oxygen, acid, flint, alloy, blast furnace, or corrosion, malleable, ductile, electrolysis, carbon, aluminium, brass, iron, copper, steel, bonding, alloy, shear force, atom, neutron, proton, electron, stiffness, elasticity, melting, fracture, creep, fatigue, crack. Building materials, environment, concrete, metal, steel, timber, insulation materials, polymers, clay, glass, gypsum, bitumen. Transparent, bendy, rigid, soft, hard, liquefied, liquefied, so bye.